Right, looks like we're diving into some serious territory today with this research you've sent us on dataset security for machine learning. Not messing around, are we?
Definitely not. It's a fascinating and, frankly, crucial area.
So, no need for machine learning 101 with this audience. We can get right into the thick of it. How about those vulnerabilities that can turn the strengths of algorithms, the math and all that, into weaknesses?
Right to the heart of it.
We're mainly looking at this 2012 paper, Dataset Security for Machine Learning, Data Poisoning, Backdoor Attacks, and Defenses. Right.
Yes, a foundational paper in this field.
It's like a digital thriller, almost. But instead of hackers and passwords, we've got malicious data points like hijacking these algorithms. Intriguing stuff.
It certainly is. High stakes, too.
So today, we're going to break down these threats, figure out how they work, and then look at what's being done to fight back. By the end, you'll have a tactical map of this whole battlefield, ready to get started.
Absolutely. Let's dive in. A good place to begin is with the attacks that happen during the training phase of a machine learning model. We call these training-only attacks.
Okay, so the attacker's basically poisoning the well before the algorithm even gets a chance to drink. Is that it?
Precisely. They don't need access to the model after it's deployed. These attacks are broadly categorized into two types: targeted and untargeted.
Targeted versus untargeted, okay.
Targeted attacks aim to make the model misbehave for specific inputs, while untargeted attacks just try to make the model perform badly overall.
Gotcha. So, for example, like a targeted attack could make a voice assistant misunderstand a specific command, while an untargeted one might just make a spam filter go completely haywire.
Excellent examples. And what's particularly concerning is that this vulnerability isn't just limited to really complex models.
Right, even a simple algorithm could be manipulated, you're saying.
Exactly. Take, for instance, the classic example of poisoning a spam filter, something like Spambaze. By flooding its training data with spam-labeled emails, but making them full of words that usually show up in legitimate emails, you can completely throw off the filter. You can't tell spam from ham anymore.
Total inbox chaos.
Yeah.
But this data poisoning thing, it's not just spam filters, right?
Oh, no, it's a much wider problem. Think recommendation systems, facial recognition, you name it. Even systems designed to be robust, like those using differential privacy or reinforcement learning, are vulnerable.
So how do these attackers actually craft these attacks? Is it like a whole arsenal of different data poisons out there?
You could say that. There's a whole range of techniques. One approach is feature collision attacks, which exploit the fact that pre-trained models are often reused, especially in transfer learning.
Ah, so they're taking advantage of shortcuts, basically.
In a way, yes.
Yeah.
And then there are even more advanced techniques, like bi-level optimization attacks.
Bi-level optimization, that sounds intense.
It is. Think of it as the attacker setting up a nested optimization problem, essentially mimicking the training process to figure out the most effective poison. Attacks like Metapoison and Witch's Brew have actually managed to poison commercial APIs, things like Google Cloud AutoML.
Wow, so even the big players aren't immune. Feels like a constant arms race.
That's a good analogy. And there are other techniques, too, like label flipping attacks, where the labels are directly tampered with.
Ah, so just straight up changing the answers, making the model learn the wrong thing.
Exactly. And then there are influence function attacks, where they analyze how specific data points affect the model's behavior.
Clever. So they're figuring out which data points have the most leverage, the ones they can use to really mess things up.
Precisely. And then there are also online poisoning, p-tampering attacks, and attacks specifically designed for federated learning.
Federated learning, that's where the data stays on individual devices, right? You'd think that would be more secure, but it sounds like it has its own set of weaknesses.
It does. The decentralized nature creates unique attack vectors. Instead of directly poisoning the data, attackers might try to manipulate the local model updates that each device sends back to the central server.
So in a way, they're poisoning the messengers instead of the message itself.
You could see it that way. This can lead to things like model poisoning, Sybil attacks where colluding agents gang up on the system, and data poisoning during the aggregation process.
Okay, so we've got these data poisoners lurking in the shadows, twisting the very foundation of these algorithms. But now let's move on to another type of threat that sounds even sneakier. Backdoor attacks.
Ah, yes, backdoor attacks. These are quite insidious. Imagine a hidden trigger embedded in the model, waiting dormant until a very specific input comes along and activates it.
So it's like a sleeper agent waiting for their code word. The model seems perfectly normal until, bam, that trigger sets off the malicious behavior.
That's a perfect analogy.
I need a concrete example here.
Yeah.
Walk me through how this could play out in the real world.
Let's imagine a self-driving car. Its image recognition system has been trained to recognize traffic signs, right? Now, an attacker could subtly modify a bunch of stop sign images in the training data, but label them as speed limit signs.
Okay, so they're teaching the car to see a stop sign but think it's a speed limit sign.
Exactly. When the car encounters a real-world stop sign with that same subtle modification, it could misinterpret it as a speed limit sign.
That is a recipe for disaster.
Hmm.
And I'm guessing this isn't just limited to image recognition, right?
Absolutely not. Backdoor attacks can be applied to all sorts of models. You could manipulate generative models to produce harmful content, or even hijack reinforcement learning systems, causing them to take unintended actions in specific situations.
So a chatbot suddenly spewing hate speech or an industrial robot malfunctioning at a critical moment. The potential consequences are pretty terrifying.
It's a serious concern, no doubt. And the techniques for creating these backdoors are quite varied, ranging from basic model agnostic attacks to highly targeted model-specific ones.
Model-specific backdoors. Those sound especially dangerous.
They are. In these attacks, the backdoor trigger is designed to exploit specific weaknesses in the architecture of the target model. For instance, they might embed a backdoor into a pre-trained model without even needing to retrain it or have access to the original data.
So they're basically planting a mole deep within the system itself.
A very apt description. And then there are clean label attacks, which are even more insidious.
Clean label? What's that about?
It's where the poison samples are actually labeled correctly, making them very hard to spot. They use techniques like feature collision to subtly skew the model's learning process, making it more reliant on the trigger for accurate classification.
So it's like setting a trap. The data itself looks innocent, but it's designed to trip up the algorithm. And I imagine this gets even more complicated with transfer learning.
Absolutely. Backdoor attacks in transfer learning are a significant challenge. If the pre-trained model is poisoned, that backdoor could stick around even after you fine-tune it on clean data for a completely different task.
So even if you think you're using a safe pre-trained model, you might be unknowingly deploying a ticking time bomb. How do they make these backdoors so persistent?
They're clever. They target specific neurons or layers in the model that are less likely to change during fine-tuning, ensuring that the backdoor survives. It requires a deep understanding of how the model learns.
So vetting those pre-trained models is absolutely crucial. And what about backdoor attacks in federated learning? Does the fact that it's decentralized make things easier or harder for the attackers?
It's a mixed bag. In federated learning, a malicious client could try to submit poisoned updates to the server.
Right, they could sneak in a bad apple with all the other updates.
Exactly. But the challenge for the attacker is that they need to gain enough influence to really impact the global model, which is being aggregated from many different clients.
So they need to be more strategic, maybe coordinate with other bad actors or try to submit disproportionately large updates.
Exactly. It becomes a game of influence within the federated learning system. On the defense side, robust aggregation algorithms are crucial for filtering out those malicious contributions.
Okay, so I've got these backdoor attacks waiting in the wings, ready to spring into action. But surely it's not all doom and gloom, right? There must be ways to fight back against these threats.
Absolutely. There are, and researchers are constantly developing new defenses to detect, repair, and prevent these attacks. We can delve into those next. So when it comes to defending against these attacks, there are broadly 3 strategies: detect the threat, repair the damage, and prevent the attack in the first place.
Okay, so it's like a 3-pronged approach.
Yeah.
Identify the enemy, fix the breaches, and then build those fortifications stronger, right?
Exactly.
Let's start with detection. We've talked about spotting anomalies in the input data itself and also in the model's internal representations, sort of like looking for red flags. What else do defenders have in their toolkit?
Well, one interesting technique is trigger reconstruction. Researchers try to actually reverse engineer the backdoor trigger from the model itself.
So they're probing the model, seeing if they can trigger that malicious behavior, and then working backward to figure out what that trigger is.
Precisely. It's a bit like code breaking, trying to decipher the enemy's secret communication.
I like that analogy.
Huh.
And are there methods that don't rely on knowing the specific trigger, sort of trigger agnostic approaches?
Yes, there are. These methods focus on analyzing the model's behavior patterns, looking for anything out of the ordinary.
Okay, so like a detective looking for those subtle clues that just don't add up. Makes sense. But what happens once you've identified a poisoned model? Is there any way to fix it, to kind of detoxify it?
There are a few techniques for repairing poisoned models. One common approach is pruning.
Pruning, like you'd prune a tree.
It's a similar idea. It involves removing neurons that are strongly associated with the trigger. Basically, you're surgically removing the infected parts of the system.
That makes sense. But wouldn't that hurt the model's overall performance?
It can, yes, but often it's a necessary trade-off. To minimize the impact, pruning is usually followed by fine-tuning on clean data. This helps the model regain its accuracy for the legitimate tasks while weakening the influence of the backdoor.
So it's like rehab after surgery, helping the model regain its strength and get back to doing what it's supposed to do.
A good analogy. Researchers are also exploring other techniques inspired by different areas of machine learning, like knowledge distillation and model compression. The idea is to distill the essence of the model, the core knowledge, while discarding those malicious components.
It's like refining a precious metal,
Yeah.
separating the pure element from the impurities. I like that. So that's detection and repair. But what about preventing these attacks from happening in the first place? That seems like the ideal scenario, right?
It is, and there are several promising techniques under development to make the training process more resilient. One such technique is randomized smoothing.
Randomized smoothing, okay. Tell me more.
It involves adding noise to the inputs during training.
So basically shaking things up a bit.
That's a good way to put it. By adding this noise, you make the model less sensitive to those subtle manipulations that attackers might try to use.
Interesting. So it can't fixate on those specific details that could be exploited. What else is there?
Another technique is using majority vote mechanisms. You train multiple models on different subsets of the data, and then you combine their predictions.
Ah, so it's like a democratic system where the majority rules. It makes it harder for a few poison data points to sway the outcome.
Precisely. And then there's differential privacy, which adds noise to the training process in a way that protects the privacy of individual data points.
So protecting privacy also has security benefits. That's a nice bonus.
Indeed, it makes the model less vulnerable to targeted attacks.
Got it. What about those input preprocessing techniques we touched on earlier?
Right, those focus on disrupting the backdoor triggers. It's like putting the data through a security checkpoint, filtering out anything that looks suspicious. Things like using autoencoders, data augmentation, or even adversarial training can be effective.
So it's like a multi-layered defense system with
Yeah.
different techniques working together to protect the model from all angles.
Exactly.
And I imagine that with federated learning, because it's decentralized, it needs some specialized defenses.
You're absolutely right. Robust aggregation algorithms are key in federated learning. They help to identify and neutralize potentially malicious updates that clients might submit.
So it's like having a security protocol for a network, making sure that no rogue agents can compromise the system.
A good analogy. And there are other defenses for federated learning too, like modifying the training protocols themselves to make them more resistant to poisoning. Differential privacy plays a role here as well by making the global model less sensitive to manipulation from any single client.
So the same principles apply, but they need to be adapted for this distributed setting. And what if, despite all these defenses, a global model in a federated learning setup still gets compromised? Is there any hope?
Yes, there are post-training defenses that can help to restore the model. They are similar to the techniques we discussed for centralized models, things like pruning, fine-tuning, or algorithms specifically designed for federated learning.
So it's like having a backup plan, just in case those frontline defenses fail. It really does feel like a constant battle, with attackers finding new ways to exploit systems and defenders working tirelessly to stay one step ahead.
It is, and it's what makes this field so fascinating and so important. The stakes just get higher as machine learning becomes more and more integrated into our lives.
We've certainly covered a lot of ground today, from understanding those different types of attacks to exploring the whole arsenal of defenses. It's clear that dataset security is a critical part of responsible machine learning.
Absolutely. Understanding these vulnerabilities and the defenses against them is essential for building systems that are robust and trustworthy.
But we've mostly focused on the technical aspects. What about the human element in all of this? Could those social engineering tactics that we see in other areas of cybersecurity be used to bypass even the most sophisticated technical defenses?
That's a great point and a very real concern. Humans are often the weakest link in any security system.
So even with the best algorithms and the strongest security protocols, a clever attacker could still exploit human vulnerabilities to get what they want.
Exactly. Imagine an attacker using phishing emails or social media manipulation to trick people into revealing sensitive information that could be used to poison a model.
Or they could infiltrate online communities where data is being shared and subtly influence the labeling or annotation process. They could introduce bias, errors, all sorts of things.
Precisely. And what's scary is that those attacks can be very hard to detect because they exploit human trust and the social dynamics.
It's a good reminder that dataset security isn't just about the algorithms and the code. It's about understanding the whole ecosystem, including the human factors that can make systems vulnerable.
And it highlights the need for comprehensive security measures that address both the technical and the human aspects of the problem.
That's a sobering thought.
Mhm.
It seems like the battle for dataset security is fought on multiple fronts.
It is. But by acknowledging these challenges, understanding the tactics used by attackers, and developing those robust defenses that account for both the technical and human elements, we can build machine learning systems that are more secure and trustworthy.
And that's ultimately the goal, right?
Yeah.
To harness the power of machine learning for good while mitigating those risks. We've given you a good understanding of the threats and the defenses, but it's up to you to continue exploring this space and staying informed as the field continues to evolve.
Remember, knowledge is power. The more we understand about these vulnerabilities and how they are exploited, the better prepared we'll be to defend against them.
Well, we've certainly delved deep into the world of dataset security today. It's been a fascinating journey exploring this hidden landscape of threats and defenses.
It certainly has, and it underscores how crucial dataset security is, not just as a technical challenge, but as a multifaceted problem that demands a holistic approach.
Right, it's like securing a fortress. You can have the strongest walls and the most vigilant guards, but if someone leaves a gate unlocked, it all falls apart.
Exactly. We need a multi-layered defense system that combines those robust technical defenses with a deep understanding of human vulnerabilities. That means implementing things like strong data handling practices, access controls, and security awareness training.
It's about creating a culture of security, where everyone involved understands the risks and takes responsibility for protecting sensitive data.
Precisely. And we can't forget that this is an ongoing process. That threat landscape is constantly evolving, so we need to stay informed, adapt to new challenges, and keep strengthening our defenses.
It's like a game of chess, where every move requires careful consideration and anticipation of your opponent's strategy.
A very apt analogy. And in this game, the stakes are incredibly high. As machine learning becomes more deeply integrated into those critical aspects of our lives, the potential consequences of a successful attack become even more severe.
From healthcare to finance to transportation, we rely on these systems to function correctly and securely.
It's our responsibility to ensure that these systems are robust, reliable, and protected from those who would seek to exploit them.
Well, we've explored the depths of dataset security today, haven't we? We've uncovered those hidden vulnerabilities, those cunning attack strategies, and the incredible defenses being developed.
We've seen how attackers can manipulate data and models, turning the very strength of machine learning against us.
But we've also seen the remarkable ingenuity of the researchers who are constantly innovating and coming up with new ways to detect, repair, and prevent these attacks.
It's a fascinating and crucial battle, one that will continue to shape the future of machine learning.
And as we wrap up this deep dive, we encourage you to keep exploring this critical field.
Stay curious, stay vigilant, and stay ahead of the curve in this ever-evolving landscape.
Thank you for joining us on this journey. May your data be safe, your models robust, and your algorithms free from malicious manipulation. It's a lot to think about, that's for sure.
Wow.
We've only just scratched the surface here, but hopefully it gives everyone listening a sense of just how important this whole area of dataset security is.
Absolutely, and it really drives home the point that dataset security isn't just some narrow technical problem, it's much bigger than that.
Right, it's really a multifaceted issue that needs a more holistic approach.
Exactly.
I keep thinking about that fortress analogy. You know, you can have the strongest walls and the most vigilant guards, but if someone forgets to lock even one gate, the whole thing can be compromised.
That's a great way to put it. We need that multi-layered defense system, one that combines strong technical defenses with a deep understanding of those human vulnerabilities.
Because at the end of the day, humans are often the weakest link.
Unfortunately, that's often the case.
So it's not just about algorithms and code. It's also about things like strong data handling practices, access controls, and making sure everyone is aware of the risks.
That security awareness training is crucial.
Creating a culture of security where everyone involved understands the stakes, and takes responsibility for protecting that sensitive data.
Exactly. And the thing is, this isn't a one and done kind of thing. The threat landscape is constantly evolving.
So we have to constantly adapt and learn.
We have to stay informed, be ready to adapt to new challenges, and always be working to strengthen those defenses.
It really is like a game of chess where every move you make has to be carefully considered. You have to anticipate your opponent's strategy.
It's a very apt analogy, and the stakes in this particular game are incredibly high.
Absolutely. As machine learning becomes more and more woven into the fabric of our lives, those consequences of a successful attack become even more serious.
Think about all the areas where machine learning is playing a critical role. Healthcare, finance, transportation, the list goes on and on.
And we're entrusting these systems with more and more responsibility every day.
It's on us to make sure those systems are robust, reliable, and protected from those who would do harm.
Well, I'd say we've taken a pretty deep dive into dataset security today. We've seen those hidden vulnerabilities, those clever attack strategies, and the incredible ingenuity that goes into developing those defenses.
We've seen how those attackers can manipulate data and models, sometimes turning the very strengths of machine learning against us.
It's a bit unsettling, to be honest.
It is. But on the flip side, we've also seen the remarkable work being done by researchers around the world. They're constantly pushing the boundaries, innovating, and coming up with new ways to detect, repair, and prevent these attacks.
That gives the hope.
It's a fascinating and crucial battle, one that will continue to shape the future of machine learning as we know it.
And as we wrap up our deep dive today, we encourage everyone listening to keep exploring this critical field. There's so much more to learn and discover.
Stay curious, stay vigilant, and most importantly, stay ahead of the curve in this ever-evolving landscape.
Great advice. Thank you for joining us on this deep dive. Until next time, may your data be safe, your models be robust, and your algorithms be free from any malicious manipulation.